Okay, so today's topic for some people is kind of tricky because people can't distinguish between the two things that I'm going to talk about. So the things I'm going to I'm going to tell you like three things. Two of them are kind of like a comparison almost. And then the last thing is it comes from like the line of best fit. So I want to start off with a quick video. This is not my video. It's from YouTube. I don't own the rights to it or anything like that. But I just want you to hear this because this is something that I think is important when it comes to deciding if something is a correlation or if it's a causation.
There's a link between coffee and diabetes, spicy food and longevity. There's also a link between Arizona's divorce rate and death by lightning strikes, and between cola consumption and car accidents. Fortunately, the word link doesn't mean much in science. Unfortunately, most people don't know that. Correlation does not imply causation. Scientists remind us of this often, and we nod like we understand them, but it pays to really know what those words mean, especially if you're trying to understand a scientific study. Because you can correlate just about any two variables in the world if you twist the numbers just right. Almost every food-related study lures you into this trap. One recent paper reported a link between spicy food and long life, after scientists found that people who ate spicy food more often tend to live longer. Several major publications covered the incredible link between chili peppers and longevity. Turns out that the fountain of youth is in a bottle of sriracha. But even the scientists who ran the study felt they might have stumbled onto a correlation, not a causation. See, the study was conducted in China, where spicy food is often a status symbol. It's likely that people who eat spicy food also have more money and better access to healthcare than people who eat bland meals. In that case, it's likely money, not spicy food, that causes long life. Let's run an imaginary study borrowed from the Spurious Correlations blog to help us understand how we keep on getting burned by bad things. Here's some national data on the number of people killed by venomous spiders between 1999 and 2009. And here's the number of letters in the winning word of the Scripps National Spelling Bee over that same time period. There's a link. But you know spelling bees don't cause spider bites, and we certainly shouldn't advise Scripps to start quizzing kids with shorter words to prevent spider attacks. It would be ridiculous to make a policy decision based on this data. It's just a correlation. Now, that doesn't mean there aren't any robust correlations out there. The link between cigarettes and lung cancer, sugar, diabetes, unprotected sex, STDs, there are also correlations, robust correlations backed up by decades of careful research. But when you see a new study that suggests an unlikely link, more often than not, it's a correlation that does not even remotely imply causation. And if anyone tells you otherwise, that's junk science.
So you can see how it can kind of be tricky because just because things are linked doesn't necessarily mean that they're caused by one another. And he went through a ton of examples. Oh, let me pause this. Hang on a second. He went through a ton of examples like the people who ate spicy foods live longer. That's just a pattern. It's just a total coincidence. There are other factors that are the cause of the people living longer. And that's what today's notes are about in the very beginning. We're talking about the difference between correlation and causation. Correlation is just like a pattern that happens between things. Doesn't necessarily mean that it's the cause. Causation is exactly that. It's what actually causes the other thing to happen. Some examples of this. When the sun rises, the rooster crows. So is that a causation or a correlation? It's just a correlation. The sun has no control over the roosters. The roosters are going to crow no matter what, probably. We just don't know because the sun always comes up every day, you know what I mean? Another one, let's see. The increase in ice cream sold and the increase in shark attacks. That's another correlation. Just because more ice cream is being sold doesn't mean that shark attacks are going to go up because of it. Now I think that example came from a YouTube video. There's a YouTube video about that. How it's not about shark attacks. It's about like increase in, I think it was in New York City or something, when ice cream sales went up, murders went up. Now, it's not saying that just because people are buying more ice cream that people are getting murdered more. There's other factors behind it that's the true cause. For example, I don't know, if the temperature goes up, people like go out and they want to, cool off, so they buy more ice cream. Just so happens that New York is super populated, it's got a lot of people, so the chances of you crossing a murderer increases also. So more people are out, they're going to want to get some ice cream, and then you've got more murderers that you could possibly cross, and then that's how that correlation sort of happens. So you have to sort of think about it, try to see if there's any other reasons why this, like one thing could happen versus the other, because sometimes it's just a coincidence, like the ice cream and shark attacks. It's just a coincidence. It's not like the sharks are watching the stocks from the ice cream companies and seeing, oh, it's a good day for ice cream, I'm going to go eat some people. It doesn't work like that. Correlations, the correlated effects, they might have a common underlying cause, and then one of the correlated effects might be the cause of the other. So I didn't put this in your notes, but you can draw it if you want to. I was sort of like trying to investigate some more examples that I could show you so you can know the difference between correlation and causation. So when we talk about germs, I found this is in your notes. When we talk about germs, germs could cause bad smells to happen. So that is a true causation. Germs could also cause people to get sick and get like a disease or something. That is a causation. But the thing is, bad smells and disease, they're both tied to germs, but that doesn't imply that bad smells cause disease. So that's not entirely true. It's just a pattern that exists. So in that situation, that would be just a correlation because it's not the true cause behind it. You guys will turn to the next page. There's a couple of examples. It says all the cases below are correlated. So there's some type of correlation, but what we need to think about is it a causation or is it just a correlation? And then we got to explain why we think that. So the number of additional calories consumed and the amount of weight gained. Do you think that's a correlation or a causation? Yeah, well, and again, it all depends on like your knowledge of like calories and gaining weight and stuff, because I think the way it's explained here, very general, it is a causation. If you eat more, usually you're going to weigh more, usually. But that's not entirely true, because you could also work out more. And then you could burn the extra calories off, and then your weight would stay the same. But the way it's explained here, I think that's a causation. Okay, the number of cars traveling on a holiday weekend and the number of accidents. Yeah, it's just a pattern that happens. In the start of the 20th century, it was noted that there was a strong correlation between the number of radios and the number of people in insane asylums. That's another correlation. It's just a wacky pattern that happened. The number of firefighters at a fire and the increased amount of damage done to the building. So I think it's probably a correlation because, I mean, think about it. Why would there be more firefighters at the fire? It's a bigger fire. So it's not the firefighters that's causing the destruction, it's the bigger fire that's causing the destruction. So that was... Yeah, I don't know about that. And then the last one, the most gruesome one I've ever read, I should have read this ahead of time. The act of decapitation in a person's death. Yeah, you cut off their head, they're gonna die. Okay, so a lot of data is not linear. It doesn't necessarily follow a pattern where it's perfect. It's scattered. So that's why we have to talk about scatter plots for a second. Now, a scatter plot just shows the relationship between two variables, and there's different patterns that could happen when it comes to scatter plots. First, you should be able to draw a line of best fit as long as there's some type of correlation. Correlation is like a pattern. The dots are all kind of going up. The dots are all kind of going down. The dots are all flat. But if the dots are scattered all over the place and you can't tell if it's going up or going down, well, there's no correlation. So you can't do a line of best fit on that one. So what we're going to talk about here, and this is the statistics part of it, because you guys have all done line of best fit before. It happens in Algebra 1. But we're going to talk about the correlation coefficient and what it means in statistics. So your correlation coefficient, you might want to underline this or put an arrow at it, because that's what the topic is. Remember I told you 3 things I was going to teach you? This is the third one. It ranges between 1 and -1. A lot of people mistake it for the slope. It's not a slope, but it does have ties to a slope. So for example, if you have a correlation coefficient of 1, the line is going up, but it doesn't necessarily mean that the slope is 1. All it means is the dots in your scatter plot are closer to being a straight line. That's all it means. Now, as you move away from 1 and you head towards 0, the closer to 0 you get, the more scattered your dots get. Brandon, check this out. If you notice, I'm going, think of it kind of like as a number line. At exactly 1, the lines are almost perfectly straight in a line, or the dots, I should say. But as I move away to 0.9, they scatter a little bit. And I go to 0.5, they scatter even more. Now at 0.5, you can still see that they're going up, but they're not as close together as the 0.9 or the 0.1. 0.1 just means that the dots are tighter in together, forming a straight line. When you get to 0, that's when there's no correlation at all. And then I said it is kind of like a slope, but not really. The only part that is similar to a slope is the positive and negative part. So if you have a negative correlation, the dots are going to head down. The closer it gets to 1, the closer the dots get to being a perfect line. So what I'm going to do, and you don't have this page, because I just put it in this morning, we're going to go through a couple of examples here. Maybe, there it is. I want to try to match up these pictures to their correlation coefficients. So is there one that we know for sure, like that we can do first? Like which one would be the easiest one to do? I think 0 would probably be the easiest one, right? What does it mean to have a correlation coefficient of 0 again? It means they're all scattered. You can't tell if it's going up or it's going down. So which one is that? The very first one. This one has a correlation coefficient of 0. They're scattered all over the place. You can't tell if it's going up or it's going down. Okay, so we're done with that one. Now, I think we can probably tell the difference between positive and negative, right? So let's talk about this one, the very next one to the right. Positive or negative? It's got to be negative. So it's either going to be this one or it's going to be this one. So let's think about what the correlation coefficient means again. What does it mean when it gets closer to 1 or -1? Closer to being a straight line. What does it mean if it gets closer to 0? It's scattered more, yeah. So is there another one in here that maybe has a negative correlation coefficient? I think maybe this one, right? So comparing these two, these are both negative. Now that we have a comparison, now we can maybe put the numbers a little bit better to match. So if these are the two negatives, which one should this top one be? It would be negative 0.8 probably. Why? Because when we compare just the two negatives, that one's closer to being a straight line. So that forces this one to be negative 0.3. So now we've got these two. And the last part, we have this positive at the top and the positive at the bottom. Which one would the top one be? 0.7, perfect. Because when you compare just the two positives, 0.7's dots are tighter in to being a straight line. So this one will probably be 0.2. One other thing I want to add, let's say this is 0.2. Think about this. Watch this. I'm going to steal this graph real quick. We decided earlier that because of the numbers they gave us, this one was 0.2. 0.2. What if I added an extra point? And let's say I put the point, I don't know, like way over here. What would that do to this number? Would it make it go up closer to 1, or would it make it go down closer to 0? Yeah, it'd probably go down because this is the general pattern of the dots. If I put a dot in there, it's probably going to stay around the same or maybe get closer to 1. But if I put a dot on the outside far away, that's making it worse. And in correlation coefficients, worse is heading towards 0. Did that make sense? Okay. Those are the 3 things I needed to teach you. The difference between correlation is just a thing that happens, not necessarily caused by the other, just a pattern or maybe even a coincidence. The second was actual causation. So the sad problem, decapitation causes death. That's directly linked. So that's causation. And then the last one is the correlation coefficient. 0 is scattered, closer to 1, and -1 is closer to being a straight line. And that's it.